Yeah, thank you, Alex. And also thank you, Helena, for organizing this very nice event. I'm very happy to be here. And I'm also happy to talk about skyrmions and actually also about objects that are related to skyrmions, but are maybe a bit better in some aspects. So Max already talked a bit about skyrmions today, but still I think it's a good idea to give you a bit of a general introduction and also to motivate why these alternative objects may be useful. So we often say that skyrmions are useful for spintronics and for data storages, for example. So the idea could be to take a hard disk drive and try to decrease the size of these ones and zeros with which you store the information. And skyrmions are very useful for this, or could be useful, because they have the so-called topologically protection. At least they have it in a mathematical model, which is a continuous model in general. And it's a bit similar to these two rings that you see here, and then you entangle them, and then it's basically impossible to disentangle them again and to end up with this configuration without breaking them. So if your magnetization density is continuous, then indeed it is impossible to destroy a skyrmion. But we know from experiments, for example, that it is possible to generate them, to destroy them, and this is because the magnetization density is discretized. So the energy barrier is not infinitely large. We do not really have this topological protection, but quite often, with the reasonable parameters, there is a large energy barrier, and then these skyrmions can be stable. And actually, in the end of my talk, I will come back to this aspect and we'll discuss a bit if this topology is important or not for the stability. But we can say that in some materials, the skyrmions are extremely stable, and so you know this idea, the racetrack idea arose to use the skyrmions to encode data. So you can write these skyrmions, and then you can read them out again, and everything works purely electrically, so without moving parts, which could be quite useful if it works someday. And besides this stability-motivated idea of the racetrack, it's also, so the skyrmions are also very interesting in terms of their emergent electrodynamics. So here we have two effects mainly, the topological Hall effect and the skyrmion Hall effect. So the topological Hall effect means that you apply an electric field, so you generate a current, and then these electrons move through the skyrmion and their spin reorients, at least partially, with the skyrmion, and so the electrons will accumulate so-called Berry phase, and after you do some mathematical transformations, you can see basically they behave as if they were under the influence of a very large magnetic field, which is called the emergent field. And in the experiment, you see that after you subtract the conventional Hall effect and the anomalous Hall effect, that there is some bump left over from your measured Hall effect data, and this can be attributed to the presence of skyrmions. So this is here the average skyrmion density. So we have this nice feature of the skyrmions, the topological Hall effect, which may be usable to detect these objects, so it's a nice hallmark. But also we have angular momentum conservation. So this means when the electron spin reorients while moving through the skyrmion texture, also the magnetic moments of the skyrmions will start to reorient. And now if you look at this collectively, you will see the skyrmion starts to move. And even in the experiment, this was, for example, done by Kai, you see that the skyrmion moves, but it does not move parallel to the current or to the field, but at an angle. And this is what we call the skyrmion Hall effect. And in this spin transfer torque scenario that I have here presented, you can say the topological charge leads to the transverse deflection. And so, of course, you can guess that it's quite bad because at some point the skyrmion may get stuck or it will even be destroyed at the edge. So much better would be that we suppress this effect and then the skyrmion moves nicely in the middle of the track and possibly even at higher velocities. So before I will present you ideas how to suppress this, let me switch the setup a bit because I do not want to drive the skyrmions by spin transfer torques but by spin orbit torques. And for this you just have to interface your ferromagnet with a heavy metal layer so that when you apply an electrical current it gets transformed to a spin current, and then you are much more efficient. So you can drive these skyrmions with smaller currents, and yeah, it's more energy efficient. And also, it's much more interesting in terms of the motion and the degrees of freedom that you have, because, I mean, we cannot go through this in detail here, but you have several terms in the effective equation of motion, and if you analyze it, you will see that it's not only the topological charge this time that's important, but that there is another very important quantity, which is this tensor, which basically describes the interaction with the spins from the spin-orbit torque. And this tensor is mainly determined by the in-plane magnetization profile of your objects. And so this means you can now consider alternative magnetic quasiparticles not only in terms of an alternative topological charge, but also more generally in terms of a different in-plane profile. And so we have considered a lot of those, and there has been many publications by many groups about these objects, and we tried to summarize them last year in this review paper. So please have a look if you're interested. And here, due to the 20-minute limitation, I can of course not talk about all of them, but I picked these 4 to be the most interesting for this talk. And I want to start here with the second row actually, which are 2 skyrmions that you have put together to form a new nano-object. So this would be the skyrmionium, which is the skyrmion inside of another skyrmion, and the antiferromagnetic skyrmion, which consists out of 2 copies on 2 separate layers, or also, if it's in a single layer, then on 2 different sublattices. And then later on, I will discuss the bimeron and the anti-skyrmion, which at first glance are more similar to the skyrmion, but as you can see, they are not rotational symmetric. So this is also quite interesting. So first, let's discuss these objects which consist out of 2 subskyrmions, and it's very easy to realize that they have a compensated topological charge. Because if you, for example, compare the top skyrmion and the bottom skyrmion, they have opposite magnetizations, and therefore they have also opposite topological charges. And the same argument also holds for the skyrmionium here. So this is a Bloch-type skyrmionium, this is a Néel-type skyrmionium, but they have the same topological charge of 0 because the inner skyrmion has the opposite topological charge of the outer skyrmion. And here I have presented to you a simulation that we did. So we created these skyrmioniums, and then we have driven them by currents, so by spin-orbit torques. And you see that overall they move nicely in the middle of the track. And yeah, there is no skyrmion Hall effect because there is no topological charge. However, if you look carefully, then you see that the central part here, which corresponds to this topological charge, will be pushed upwards, and the outer ring also deforms and will be pushed downwards. And this imposes a new problem because if you increase the current too much, then these forces become too strong, and then the skyrmionium will just unzip. And actually, it turns out in the simulation, the skyrmionium is not much more useful than the skyrmion. However, the idea is nice, I think, and it is improved by the antiferromagnetic skyrmion. Because here, everything follows the same logic. You have these 2 subskyrmions that are pushed along different transverse directions so that it compensates overall. But since these sublattices are intertwined, you have a much higher stability, and you can apply higher currents and they will remain stable. So in principle, in theory, they are much better and they can move at higher speeds and are much more stable. And there has been a lot of research over the last couple of years, even experimentally, and I only want to present here our contribution, which was that we have simulated by Monte Carlo a periodic lattice of these antiferromagnetic skyrmions. So this is a antiferromagnetic skyrmion crystal. And to maybe help for the detection, we have thought about hallmarks for this phase. And at the same time as the group of Yuri Mokrusov, we have predicted a topological spin Hall effect. So here the idea is that you do not have a topological Hall effect, so not based on the charge, but the spin version based on the spin. And so the simple explanation would be you have the 2 sublattices, and let's consider first the top one. So here you have electrons, let's say, going to the left, and the net magnetization is negative. And here on the other sublattice, you have the opposite topological charge, so the electrons go to the right. And since the net magnetization is now upwards, you have basically 2 spins going along different transverse directions. So you have this typical spin Hall effect scenario. So this could be maybe a nice hallmark to help detecting these antiferromagnetic skyrmions in the experiment. But I think in terms of the current-driven motion, the skyrmionium and the antiferromagnetic skyrmion are quite easy to understand because you have this compensated topological charge. What was much more surprising for me in the beginning was when I've considered these anti-skyrmions and bimerons, which are objects that still have a finite topological charge, but they have a lower symmetry, so they are not rotational symmetric. as compared to these objects here, for example. And so I mentioned this already earlier. What it does is it gives you a different tensor in the equation of motion. And essentially, it means that you still have this gyroscopic force, which originates in the topological charge, and it's still always perpendicular to the velocity. But now you can reorient this force. And so you can find a specific setup where the transverse component of this force compensates the gyroscopic force. And then everything still moves without the Skyrmion Hall effect. And in reality, it means you have to apply the current along a specific direction. Or, experimentally speaking, you have to grow your sample along, or prepare it along a specific crystallographic direction. And now I want to talk a bit more detail about these two objects, the Bimeron and the anti-skyrmion. And so first about the Bimeron, this is basically an in-plane skyrmion. So we can start from the skyrmion here and then apply a simple transformation. We basically take every magnetic moment here and rotate it by 90 degrees around this axis. So for example, this blue spin pointing up now points to the right, so it becomes this one, is now in the plane. And for example, this white spin here pointing to the right will now point downwards, so it becomes this red spin. And this transformation leaves the topological charge invariant, so it means the Bimeron still has the same topological charge as the skyrmion, which is why we can also call it in-plane skyrmion. However, if you just look at it, you see I've indicated it here by colors. It consists out of an antimeron and a meron, so this is why we also call it the Bimeron. And I've already talked about the advantages in terms of the current-driven motion. If you apply a current along a specific direction, you can have a vanishing Skyrmion Hall effect. And as you can see, in the same year as we've predicted those, they have also been observed in the experiment. So why are these Bimerons interesting? Well, of course, because they have this nice current-driven motion, but also because we can carry over a lot of the results and experiences from the skyrmions. So for example, the phase diagram looks very similarly, at least in a frustrated model. So we can now apply an in-plane magnetic field instead of an out-of-plane magnetic field, and it gives us the same phases. We have here a spiral phase, a bimeron crystal phase, individual bimerons, and then the ferromagnet. And the reason for this is, if you compare these two, this one has an out-of-plane net magnetization, and this one has an in-plane net magnetization. And for the same reason, also the topological Hall effect is interesting because they have the same emergent field, since they have the same topological charge. So we expect same, or at least very similar topological Hall effect, but we can expect quite different conventional and anomalous Hall effects, because here we have now the net magnetization and the stabilizing field in the plane. So at least by this typical experimental argument, you would say it enters a different tensor element, even though we know that in reality it's probably a bit more difficult. All right, so Bimerons are interesting, and anti-skyrmions also interesting because, yeah, they are also not rotational symmetric, so current direction matters. And you see, they consist out of Bloch parts and nail parts. And for example, if you apply the current along the Bloch part or the nail part, it will give rise to a different Skyrmion Hall angle, and you can find a specific direction where this Skyrmion Hall effect is absent. And so here, Jagannath Jena, who is a postdoc now in the group of Stuart Parkin in Halle, he has prepared these samples, and at least from the theoretical prediction, it would now follow that in some particular sample there is no Skyrmion Hall effect. However, in reality, these objects do not move yet, so we have to improve here a bit more. All right, so still, I want to summarize this part, the current-driven motion. So we have found several options to suppress the Skyrmion Hall effect, but actually, this is not the only problem of a racetrack. So yeah, this is one of the main problems, but we also have another one, which is that when we write such a sequence here and wait for a long time, then the skyrmions interact with each other, and they will form an equidistant sequence, which means that your information has been changed or is essentially lost. So it makes the whole device useless. And so the main idea to suppress or to overcome this problem is to build a racetrack based on several objects. And we have seen that in a Heusler material, skyrmions and anti-skyrmions can coexist at the same time. But maybe let's make it a bit more slowly. We have first analyzed low temperatures, so something around 200 here in this case. And Jagannath has seen in the Lorentz TEM that we have these elliptical Bloch-like skyrmions. At least according to my simulation, this corresponds to the Bloch skyrmions. And then for the higher temperatures of 300 Kelvin, we see these 4-spot signals in the Lorentz TEM, which corresponds to anti-skyrmions. And so then, of course, the idea was, let's go to an intermediate temperature. This was about 268 Kelvin. And as you can see on the right, we see the coexistence of several of these objects. For example, here we have such an elliptical skyrmion. Here we have a square-shaped anti-skyrmion. And we even see topologically trivial bubbles, even in 2 varieties, one pointing in this direction and this one pointing in that direction. That's really a unique finding, which is not possible in typical skyrmion hosts, that we have this coexistence. And to explain to you just briefly how the coexistence works or where it comes from, we have to understand the interaction. So, you know, the typical interaction that stabilizes the different types of skyrmions is the DMI, and it's generated from spin-orbit coupling and a broken inversion symmetry. And now it makes a huge difference how this inversion symmetry is broken. For example, we have these manganese silicide B20 materials. You have a bulk-like DMI which stabilizes Bloch skyrmions. At interfaces, you have an interfacial DMI stabilizing Néel skyrmions, and in these Heuslers, you have an anisotropic DMI, which just means when you look at the magnetic atoms and you go along different crystallographic directions, you see there's a different environment, and this will generate anisotropic DMI vectors, and ultimately stabilizing this anisotropic texture, this anti-skyrmion. But like in every magnetic material, also in the Heuslers, we have the dipole-dipole interaction. And even in centrosymmetric materials where there is no DMI, we have this interaction, and we see even there the dipole-dipole interaction can stabilize skyrmion-like objects. These are these Bloch-type bubbles. And they even come in 2 varieties, so white and dark, and this means right-handed and left-handed helicity. And so now if we put both of these ingredients together, and I've seen in my simulation when I started from a circular anti-skyrmion and from a circular Bloch skyrmion, all of these objects remain stable. And this is, of course, because we have the DMI favoring the anti-skyrmion and the dipole-dipole interaction favoring the skyrmion with the opposite topological charge. And then we also see that we have this deformation, like in the experiment. And this comes, or this can be explained if we consider the other interaction like a perturbation. For example, here we start from an anti-skyrmion and then consider the dipole-dipole interaction, which favors the Bloch parts like a perturbation. So we increase the ratio of the Bloch parts versus the Néel parts, and so we end up with this square-shaped deformation. And a similar argument can be found for the elliptical deformation of the Bloch skyrmions. And while this coexistence of these objects is very interesting, we have also found that at the edges of these Heusler materials, there's another very interesting phenomenon happening, which we have not seen before in typical skyrmion hosts. And this is the observation of fractional spin textures. So for example, at the higher temperatures where we have anti-skyrmions in the bulk, we see at the edge these triangles. And if we compare it with the micromagnetic simulations, these are basically anti-skyrmions which have been cut in half. So this is, I would say, totally unexpected from the continuous model, because these objects have a topological charge that's not integer, and still they can be stable. And even for lower temperatures, where we have these elliptical skyrmions in the bulk, we also see that they can exist cut in half at the edge. And so just to make my statement a bit more precise, they are not really cut in half. If you calculate the topological charge, it's not even 0.5, but in this case, it's 0.42. So that's why we call them fractional spin textures. Still, they are very stable just for the simple reason that if you think about it, how would this object here be destroyed? Well, it could either extend into the bulk, which is not possible because we have there already anti-skyrmions, so there is no space left, or it could be pushed outwards. However, this is not possible because we have this twist of the texture at the edge. And this twist is really induced by the anisotropic DMI, or is characterizable by this anisotropic DMI, and therefore this Heusler material only allows for hosting these fractional spin textures in this case. So once again, a very interesting finding and very different compared to typical skyrmion hosts. And so this got me thinking, and this leads me to my last slide. If we have here the observation of fractional spin textures, which should not be stable in terms of a continuous mathematical model, is the topological charge so important? And so I decided to look again at the topologically trivial bubbles in these materials. And I've seen, in the simulation at least, they are just as stable as the skyrmions or the anti-skyrmions. And if you look at it, you can see they come in 4 different varieties, and always they are just the composite of half an elliptical skyrmion and half a square-shaped anti-skyrmion. And yeah, they can also be stable. They have different in-plane magnetizations, which means they can be not only detected, but also distinguished. And the nice thing is they have been observed by Tokura's group, and they solve both of the problems of the racetrack at the same time. So since they don't have a topological charge, they show no skyrmion Hall effect. And since we have multiple of those, which can even coexist, we can, in principle, construct such a racetrack based on several carriers of information. And since we do not only have 2, but 4, then this even increases the storage density. So I personally think that it could really be worth it to look again at these bubbles, but not in the typical dipole-dipole bubble racetrack idea, but in these Heusler materials, because they seem to behave a bit differently and are much more stable. And with this, I'm at the end of my talk, and I just want to briefly summarize. I've talked about these objects, and I have discussed the compensation of the skyrmion Hall effect, unusual electrical signatures, and the coexistence of several nano-objects. And I want to thank all of the collaborators that helped enormously, especially Jagannath, and I want to thank you for your attention.